Okay, so today I am going to show how we are using the software R to solve the problem that I mentioned in my last video. So here is the problem that I had. So I had this system, it's approximate linear system. The first column was 342, the second column was 413, and the measurement vector was 9.8, 9.1, then 7.0. So in order to solve it using R, let's start R first. I am using Ubuntu. So I am starting it from the command line. You might be using some other thing. If you are using Windows, you might be double clicking some R icon or starting from R Studio. So personally, I prefer to use just plain R instead of R Studio. So the first thing that I will do is to create the coefficient matrix. So let me call that X. So X is matrix. I have to enter it column by column. So I will create the matrix C 3, 4, 2, 4, 1, 3. The C that I have written, that means you create a vector. So you just create a vector of these numbers. So that's what I am showing. Oops, what am I doing? So I am just creating a vector of these numbers. And I have specified all the numbers column by column. So 3 first, then 4, then 2, then 4, then 1, then 3. Now I have to wrap all these things up in a matrix. I will specify the number of rows, that is 3, and number of columns, that is 2. And that will give me my X. Let's see. X, enter. That is indeed 3, 4, 2, 4, 1, 3. These are the row numbers and these are the column numbers. And then what I will do is I will create this measurement vector. I will call that Y. Now I do not need the matrix command, just this will C will do 9.1, 7.0, and that is my Y. Now I am going to create this model, and the way to create that model is somewhat strange. I will have to start with the measurement vector, that is Y. And then I will have to put a tilde. This tilde basically stands for this approximate equality. Then I will have to write X. So that is, roughly speaking, this particular model. So this is the right hand, this is the measurement vector, not the right hand vector. In this case I am writing in the left hand. That's always the rule. You first start with the measurement vector, then the approximate equality represented by tilde, then that coefficient matrix. There are other ways of writing it also. We are going to see that, but this is the simplest form. And I am going to solve it as a linear model. So I will write LN, that stands for linear model. Now comes the weird part. I have to write a -1 after this. I will explain the -1 in a moment. Now this is the command. I will hit enter and I will get the values. X1 2.0378 and X2 0.9411. What this means is that it has estimated in the least squares way the value of A and the value of B. So A turns out to be 2.0378 and B turns out to be 0.9411. That's it. Now I will explain why I needed that -1. So what it does, that is not very difficult to see. I will just store this result in something called a variable fit. So I just created a variable called fit and stored the result of ln inside that variable. Now I will see what is the coefficient matrix that fit uses. The command for that is model.matrix. And model.matrix is indeed the matrix that we had given. Ignore for the time being those ATTR, assign, etc. So it is 3, 4, 2, 4, 1, 3 as it should have been. Now let us see what it would have been had I not used that -1. So I will replay that command. In order to replay the command, I will not type everything but simply press the upward cursor key of my keyboard to get the last command that I printed. Press it again and I will get to the command before that, and I will remove that X. Let's give it a different name, phi2. I will again go through that model matrix line, and you will see in this case the matrix is different. It is basically the same as before. We do have the 3, 4 and 4, 1 and 2, 3, but it has appended one additional column of 1 at the beginning. And that is a habit of R which might appear to be weird at present, but once we learn a little bit more of linear model, we will see that this is actually a helpful behavior, that R will by default append a column of 1 in front of the matrix which you specify. In order to prevent R from doing that, we have to put that -1. Now look carefully at this formula object. Such a thing is called a formula in R. X -1 actually has a very special meaning. It does not mean subtract 1 from each entry of the matrix as you might have expected. This means that do not append an additional column of 1. So whenever you are writing a formula object, remember that the traditional arithmetic operators do not have their usual meaning after that tilde notation. We are going to learn later about the details, about the syntax of this formula object in greater details, but for the time being, just enough to know that if you have the measurement vector and if you are ready to specify the entire coefficient matrix, then you can always use the LM function in this way to solve the least squares problem. Now, one reason why we use the LM function and not direct computation using that X transpose X thing is because the LM function is more numerically stable. That is something that you will not readily realize because you will get the same answer in such a simple case. But if your design matrix, that matrix is called the design matrix, that capital X matrix, is such that X transpose X is nearly singular, that is, this determinant is non-zero, but pretty close to 0. In that case, this LM function will give you better result than using directly computing X transpose X and all that. So in our case, let's just quickly carry out that operation also. So what I will do is that I will write down that thing X transpose X, so X transpose, and I will multiply this with X, that is the multiplication sign, star hash, star and percentage star percentage X. So I created that matrix, and let me put that in some M. So let's see what M is. So M is this. X transpose X is this 2 by 2 matrix, 29, 22, 22, 26. It's symmetric, of course. And let me also create N, that is, what's that? That is transpose of X matrix multiplication of Y, that is N. So we want to solve M beta equal to N. So this is the system that we are trying to solve, M beta equal to N. That is not our syntax, so it's a comment. So I will write it as a comment. That hash makes it a comment. So this is what we are trying to solve, and we know that the thing that we will get is beta hat is M inverse N. So let's just see whether I can do that. The way to solve a system in R is to use the function solve M comma N. I use solve M comma N, and these are the values that I get. Let's compare it with the fit that I had earlier. So I will just quickly go to that line. LM, this is the thing that I had used. Indeed, I got basically the same thing. 2.0378 is what I got from LM, and here I get 2.0377 blah blah blah. Here I had got 0.9411 and here I had 0.941111. So in this case I got the same answer using LM and directly by the brute force formula. So you might think that what is the use of using LM? I have already told you that this is numerically more stable. It does not use direct matrix inversion, which is a numerically unstable operation. However, there is another reason which is more important. Suppose your design matrix, the X matrix, is such that X transpose X happens to be a singular matrix. Let's just quickly create one such thing. Suppose I give you this X matrix. So I had this X matrix earlier. Where was that line that I typed? This was the line. I have 3, 4, 2, 4, 1, 3. So what I will do is I will just do the following: 3, 4, 2, and I will make this again 3, 4, 2. So my new X matrix is 3, 4, 2, 3, 4, 2. And if you now want to compute X transpose X, let's just see that. This is my X transpose X. 29, 29, 29, 29. You have no doubt that this is a singular matrix. And let's compute my N once again. I had my last N, that is my N. And I will do the same old story again, solve Mn, and I get an error because that is a singular matrix. It says system is exactly singular and some u22 equal to 0, whatever. Now let us try to apply Lm in this case. So Lm y tilde x minus 1. And you see, it still gives you an answer, but the answer is interesting. It says x1 is 2.752, x2 is Na, which means it has figured out that this system does not have a unique solution. However, the set of normal equations is always consistent. So if it does not have unique solution, it means it has got infinitely many solutions. So you can arbitrarily set some of the variables carefully chosen equal to 0. Now the Lm function cleverly figures out that it can set the value of the second variable, that is the coefficient of x2. Remember, x is my matrix consisting of these two columns. So x2 is the second column. So the coefficient of that is what it reports under x2. So in our example it is b. It sets b equal to 0, and then of course it can solve uniquely for a. Since it has set b equal to 0 arbitrarily, so instead of reporting that as 0, it is reporting that as Na. Na means not applicable. So it says that if I set arbitrarily b equal to 0, then I can solve for a. So the presence of the Na indicates that this system is actually not non-singular. There are infinitely many solutions, and it also gives you one particular solution of this. So that is one reason why Ln is preferable over the direct that X transpose X inverse thing. So you have learned two reasons why Lm is preferable. One is numerical stability, which is not apparent in this example, and the other one is that it can handle non-unique solutions in a smart way. There is another reason, the third reason, which happens to be the most important reason, is that in this case we specified the entire matrix directly. Now in many cases this matrix will be huge, something like 1000 rows is not unusual, and the matrix will also be complicated, so typing out everything by hand is difficult. Then Lm can actually construct the matrix from U if we specify certain structure of the matrix, and that's how we do it most of the time, and we shall see how to specify certain commonly occurring structures easily such that the LM function will construct the design matrix internally on its own. But for the time being, that's all that I wanted to say in this video.